Determining the maximum breaker size for 7.5 horsepower three-phase motor involves understanding the National Electrical Code, the motor's full load amps, and the ampacity of the conductors feeding the motor. The full load amps, or FLAW, of the motor is given as 24 amps. The conductors are number 10 THHN. The goal is to select a breaker that protects both the motor and the conductors from overcurrent, but allows the motor to start without tripping the breaker due to immersed current. According to the NEC, the maximum breaker size for motor branch circuit protection is determined by multiplying the motor's FLA by a certain percentage. For inverse time circuit breakers, this percentage is typically 250% of the motor's FLA. Therefore, you would multiply 24 amps by 2.5, which equals 60 amps. However, NEC 430.52 provides guidance on maximum overcurrent protection device ratings for motors. It states that if the calculated value doesn't correspond to a standard breaker size, you can go up to the next standard size. Standard breaker sizes are typically 15, 20, 25, 30, 35, 40, 45, 50, 60, 70, 80, 90, 100 amps and so on. While the calculation results in 60 amps, it's crucial to consider the ampacity of the number 10 THHN conductors. THHN wire has an insulation type that is rated for 90 degrees Celsius in dry locations, but its ampacity is often determined by the termination temperature rating of the equipment to which it is connected, which is commonly 75 degrees Celsius. AEC Table 310.16 provides ampacities for conductors based on insulation type and temperature rating. When using the 75 degrees Celsius column, number 10 THHN copper conductors are typically rated for 30 amps. This is a very important consideration because the overcurrent protection device, or the breaker, needs to protect the conductors from overload. If the breaker is sized too high, it may not trip in time to prevent the conductors from overheating and potentially causing a fire. Therefore, the breaker size must be less than or equal to the conductor ampacity. Given that number 10 THHN is rated for 30 amps at 75 degrees Celsius, the maximum breaker size should not exceed 30 amps. Now let's consider the motor protection aspect. NEC 430 covers motor circuits and overload protection. While a 30 amp breaker is suitable for protecting the conductors, it's also important to ensure that the motor has adequate overload protection. Overload protection is designed to protect the motor from running at excessive current levels for extended periods, which can damage the motor windings. Overload protection is typically provided by overload relays or devices that are separate from the branch circuit protection. These overload devices are designed to trip at a lower current level than the branch circuit breaker, providing more sensitive protection for the motor. The overload protection is sized based on the motor's nameplate FLA. For motors with a service factor of 1.15 or higher, or a temperature rise of 40 degrees Celsius or less, the overload protection should not exceed 125% of the motor's FLA. For motors without these service factors or temperature rise, the overload protection should not exceed 115% of the motor's FLA. In this case, assuming the motor has a service factor of 1.15 or higher, the overload protection should not exceed 1.25 times 24 amps, which equals 30 amps. So, the overload protection can be set to 30 amps. It's important to note that the branch circuit breaker and the overload protection serve different purposes. The branch circuit breaker protects the conductors from overcurrent due to short circuits or ground faults, while the overload protection protects the motor from overheating due to prolonged overloads. In summary, the maximum breaker size for a 7.5 horsepower three-phase motor with a FLA of 24 amps, fed with number 10 THHN conductors, is limited by the ampacity of the conductors. Since number 10 THHN is rated for 30 amps at 75 degrees Celsius, the maximum breaker size should be 30 amps. While the NEC allows for a higher breaker size based on the motor's FLA, the conductor ampacity is the limiting factor in this case. It is crucial to select a breaker size that protects both the motor and the conductors from overcurrent. In addition to the branch circuit breaker, It's also important to provide adequate overload protection for the motor to prevent overheating and damage to the motor windings. This overload protection should be size based on the motor's nameplate FLA and should be coordinated with the branch circuit breaker to ensure proper protection of the motor and conductors. Remember to always consult the NEC and local electrical codes for specific requirements and to ensure compliance with all applicable regulations. Also, ensure the electrical work is performed by a qualified electrician. Now let's consider the effect of ambient temperature on the conductor ampacity. The ampacity of conductors listed in NEC Table 310.16 is based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature is higher than 30 degrees Celsius, a correction factor must be applied to the conductor ampacity. These correction factors are listed in NEC Table 310.15b2. For example, if the ambient temperature is 40 degrees Celsius, the correction factor for THHN conductors is 0.91. This means that the ampacity of the number 10 THHN conductor must be multiplied by 0.91. In this case, the adjusted ampacity would be 30 amps times 0.91, which equals 27.3 amps. Therefore, if the ambient temperature is 40 degrees Celsius, the maximum breaker size should be reduced to 25 amps to protect the conductors from overheating. It is also important to consider voltage drop in the circuit. Voltage drop occurs when the voltage at the motor terminals is less than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can cause the motor to overheat and operate inefficiently. The NEC recommends limiting voltage drop to 5% for power circuits. To calculate voltage drop, you need to know the length of the circuit, the conductor size, the current flowing through the circuit, and the voltage of the circuit. There are voltage drop calculators available online that can help you calculate voltage drop. If the voltage drop is excessive, you may need to increase the conductor size to reduce the impedance of the circuit. Another factor to consider is the type of enclosure used for the motor starter and the disconnect. The enclosure must be rated for the environment in which it is installed. For example, if the enclosure is installed in a wet location, it must be NEMA 4 rated to protect the electrical components from water damage. Similarly, if the enclosure is installed in a hazardous location, it must be rated for the specific hazardous environment. It is also important to ensure that the motor starter and disconnector are properly sized for the motor. The motor starter must be capable of handling the motor's starting current and running current. The disconnect must be capable of interrupting the motor's full load current. In addition to the NEC, there may be local electrical codes that apply to the installation. It is important to consult with a local electrical inspector to ensure that the installation complies with all applicable codes and regulations. It is also important to follow the manufacturer's instructions for the motor, motor starter, disconnect, and other electrical components. The manufacturer's instructions provide important information about the installation, operation, and maintenance of the equipment. Finally, it is important to perform regular maintenance on the motor and electrical system to ensure that it is operating safely and efficiently. This includes inspecting the motor windings, bearings, and connections, as well as testing the overload protection and branch circuit breaker. By following these guidelines, you can ensure that the motor is properly protected and that the electrical system is operating safely and efficiently. Therefore, to reiterate, the maximum breaker size should not exceed 30 amps. Now let's delve into some additional considerations for selecting the appropriate breaker size and ensuring motor protection. We've already discussed the importance of conductor ampacity and adhering to the NEC guidelines. However, real-world applications often present unique scenarios that require a more nuanced approach. Firstly, consider the motor's starting characteristics. Motors draw significantly higher current during startup than during normal operation. This inrush current can be several times the motor's FLA. A standard circuit breaker might trip unnecessarily due to this inrush current, even if the motor is operating within its normal limits. To address this, the NEC allows for the use of inverse time circuit breakers or fuses specifically designed for motor applications. These breakers have a time delay characteristic that allows them to withstand the temporary inrush current without tripping. However, they still provide overcurrent protection in the event of a sustained overload or short circuit. The specific type and rating of the breaker or fuse should be selected based on the motor's starting characteristics and the recommendations of the motor manufacturer. Secondly, consider the altitude at which the motor is installed. At higher altitudes, the air is less dense, which could affect the motor's cooling capacity. This can lead to the motor overheating, even if it is operating within its normal current limits. To compensate for this, the motor's FLA may need to be derated at higher altitudes. The derating factor will depend on the altitude and the motor's design. The motor manufacturer's specification should provide guidance on derating the motor for altitude. Thirdly, consider the presence of harmonics in the electrical system. Harmonics are distortions in the sinusoidal waveform of the alternating current. They can be caused by nonlinear loads, such as variable frequency drives, electronic ballasts, and computers. Harmonics can increase the current flowing through the conductors and the motor, leading to overheating and premature failure. If harmonics are present in the electrical system, it may be necessary to use oversized conductors and harmonic filters to mitigate their effects. The specific measures required will depend on the severity of the harmonic distortion. Fourthly, consider the type of load that the motor is driving. Some loads, such as pumps and fans, require a constant torque throughout their operating range. Other loads, such as compressors and conveyors, require a variable torque. The type of load can affect the motor's current draw and the required breaker size. For example, a motor driving a constant torque load will typically draw a higher current than a motor driving a variable torque load. Fifthly, consider the coordination of overcurrent protection devices. In a multi-motor system, it is important to coordinate the overcurrent protection devices to ensure that a fault on one motor does not trip the breakers for other motors. This can be achieved by using selectively coordinated breakers, which are designed to trip in a specific sequence to isolate the fault. Selective coordination can improve the reliability of the electrical system and prevent unnecessary downtime. Sixth, consider the use of motor protection relays. Motor protection relays are electronic devices that provide comprehensive protection for motors. They can monitor various parameters, such as current, voltage, temperature, and vibration, and trip the breaker if any of these parameters exceed preset limits. Motor protection relays can provide more sensitive and reliable protection than standard circuit breakers. They can also provide valuable information about the motor's operating condition, which can be used to prevent failures and improve maintenance practices. Seventh, consider the impact of single phasing. Single phasing occurs when one of the three phases of a three-phase motor is lost. This can cause the motor to overheat and fail quickly. Some motor protection relays are equipped with single phasing protection, which will trip the breaker if single phasing is detected. Single phasing protection can significantly extend the life of the motor. Eighth, consider the importance of proper grounding. Proper grounding is essential for electrical safety. It provides a low impedance path for fault current to flow back to the source, which helps to trip the breaker quickly and prevent electrical shock hazards. The grounding system should be installed in accordance with the NEC and local electrical codes. Ninth, consider the use of surge protection devices. Surge protection devices protect electrical equipment from voltage surges caused by lightning strikes, power line switching, and other events. Voltage surges can damage the motor windings and other electrical components. Surge protection devices should be installed at the service entrance and at the motor to provide comprehensive surge protection. 10th, consider the importance of regular inspections and maintenance. Regular inspections and maintenance are essential for ensuring the safe and reliable operation of the motor and electrical system. This includes inspecting the motor windings, bearings, and connections, as well as testing the overload protection and branch circuit breaker. Any problems should be corrected promptly to prevent failures and ensure electrical safety. These considerations, while not exhaustive, highlight the complexity of selecting the correct breaker size and ensuring comprehensive motor protection. A qualified electrician should be consulted to assess the specific application and ensure compliance with all applicable codes and regulations. Remember that electrical work can be dangerous, and it should only be performed by qualified personnel. It's important to consult the specific requirements outlined in the NEC and any applicable local codes. These codes provide detailed guidelines for selecting overcurrent protection devices, conductor sizing, and other aspects of motor circuit design. Local authorities having jurisdiction or ODs may also have specific requirements that must be followed. In addition to the NEC, the motor manufacturer's specification should also be consulted. The manufacturer's datasheets provide important information about the motor's FLA, starting current, and other characteristics that are essential for selecting the correct breaker size. The motor manufacturer may also recommend specific types of breakers or fuses that are best suited for the motor. The selection of overcurrent protection devices should be based on a thorough understanding of the motor's characteristics, the application requirements, and the applicable codes and regulations. A qualified electrician can perform the necessary calculations and assessments to ensure that the motor is properly protected and that the electrical system is safe and reliable. Remember that electrical safety is paramount. Always energize circuits before working on them and follow all safety precautions. If you are not qualified to perform electrical work, hire a qualified electrician. They will ensure that the work is done safely and in accordance with all applicable codes and regulations. When selecting a breaker for a motor circuit, several other factors should be taken into account to ensure proper protection and avoid nuisance tripping. Firstly, consider the ambient temperature in the location where the breaker is installed. Breakers are typically rated for a specific ambient temperature, and their current carrying capacity may be reduced if the ambient temperature is higher than the rated value. If the breaker is installed in a hot environment, it may be necessary to use a breaker with a higher current rating to compensate for the dirting. Secondly, consider the altitude at which the breaker is installed. At higher altitudes, the air is less dense, which can affect the breaker's ability to dissipate heat. This can lead to the breaker overheating and tripping prematurely. If the breaker is installed at a high altitude, it may be necessary to use a breaker with a high current rating or to provide additional cooling. Thirdly, consider the presence of harmonics in the electrical system. Harmonics are distortions in the sinusoidal waveform of the alternating current. They can be caused by nonlinear loads such as variable frequency drives, electronic ballasts, and computers. Harmonics can increase the current flowing through the breaker, leading to overheating and tripping. If harmonics are present in the electrical system, it may be necessary to use a breaker that is specifically designed to handle harmonic currents. Fourthly, consider the coordination of overcurrent protection devices. In a multi-motor system, it is important to coordinate the overcurrent protection devices to ensure that a fault on one motor does not trip the breakers for other motors. This can be achieved by using selectively coordinated breakers, which are designed to trip in a specific sequence to isolate the fault. Selective coordination can improve the reliability of the electrical system and prevent unnecessary downtime. Fifthly, consider the type of load that the motor is driving. Some loads, such as pumps and fans, require a constant torque throughout their operating range. Other loads, such as compressors and conveyors, require a variable torque. The type of load can affect the motor's current draw and the required breaker size. For example, a motor driving a constant torque load will typically draw a higher current than a motor driving a variable torque load. Sixthly, consider the duty cycle of the motor. The duty cycle is the percentage of time that the motor is running versus the total time. If the motor is running continuously, it will draw more current than if it is only running intermittently. The breaker size should be selected based on the motor's continuous current draw. Seventhly, consider the starting method used for the motor. Different starting methods, such as across-the-line starting, reduced voltage starting, and variable frequency drives, have different starting current characteristics. The breaker size should be selected based on the motor's starting current and the starting method used. Eighthly, consider the type of enclosure used for the breaker. The enclosure must be rated for the environment in which it is installed. For example, If the enclosure is installed in a wet location, it must be NEMA4 rated to protect the electrical components from water damage. Similarly, if the enclosure is installed in a hazardous location, it must be rated for the specific hazardous environment. Ninthly, consider the interrupting rating of the breaker. The interrupting rating is the maximum fault current that the breaker can safely interrupt. The interrupting rating must be high enough to handle the available fault current at the point of installation. Tenthly, consider the listing and labeling of the breaker. The breaker must be listed and labeled by a recognized testing laboratory such as Underwriters Laboratories or all. The listing and labeling indicate that the breaker has been tested and meets applicable safety standards. By taking these factors into account, you can select a breaker that will provide proper protection for the motor and the electrical system. Remember that electrical work can be dangerous, and it should only be performed by qualified personnel. If you are not qualified to perform electrical work, hire a qualified electrician. They will ensure that the work is done safely and in accordance with all applicable codes and regulations.